Okay, so leftovers from last time. So hopefully we go through this, and then I have a very fun thing for today. Is it today or not? Okay, so this is the one that we're skipping. We have problems, but suddenly there's a bad contact there somewhere. We don't want to touch it anymore because it suddenly works. Don't touch, please. I don't want. So now it works, and I'm gonna.
Maybe it should be until 8 p.m. because it might not work.
So be on standby because we might need you again. And then we're going to try to process some data and plot some graphics. All right. So list comprehensions. This is a very interesting feature of Python. It's imported from Haskell. If you happen to know Haskell, then you would find this familiar. And it is very mathematical in nature, right? So it's a way of expressing collections based on a property. Okay? So, for instance, we can get the list of all the squares between 1 and 10 by saying x square for x in range 10. Right? So this will produce the result actually from 0 to 9, not from 1 to 10, from 0 to 9 square. All right? And what's going to happen is that this range is traversed in order. This expression is computed. All right? And all the results are collected into a similar collection. All right? So we're using square brackets, and this is a list. 2 to the power of I up to the from 0 to 12. And we're going to get something similar, right? All the powers of 2. All right? And why did I write this twice? Oh, the second one is a set, right? So we can use it with lists. Whenever we use square brackets, it's a list. If we use it with curly brackets, it's a set. All right? When we do it with a set, we would see the elements in random order. Remember, the set doesn't keep order. Also, it is possible that this function, it's not the case right now, but it's possible that this function is not injective, right? So it may have the same value for multiple arguments. And in that case, only one instance would be kept in the case we use a set, right? So this is a place where the distinction between set and list is important. We can add clauses, right? We can filter elements and not keep all of them. So for instance, if we want to get the squares of all the even numbers between 1 and 10, between 0 and 9, between 0 and 9, right? We can add a clause here, and there's an extra bracket that is wrong. All right, so, oh no, sorry. So I can do extra filtering, right? But actually, this is a very complicated way of doing things. I wonder why I did that. So one thing that we can notice from this is that we can use them in a nested fashion, but you wouldn't write this in this way, right? What you want to write is this, okay, which does the same thing. Okay, so the previous expression illustrates the fact that we can use the range, we can use these notation in a nested way, but we can do it in a simpler way. All right, so remember the if clause performs filtering. Very often what we do is we generate elements, filter out of them, and keep only some. It's a very typical pattern. All right, and we can use it in a nested fashion, and we can use multiple fors and multiple ifs. All right. So what we have here is I think I was trying to get to so this would be primes, right? And let's see why these are primes. So we want to take a range of numbers. We want to filter out some elements, right? So which elements do we want to filter out? And we want to get, we're guessing this number, right? Why are we guessing this number? Because we're going to eliminate all elements. Let's make this equal to 100. It's easier to explain, right? So we want to eliminate all the multiples of any number. That's what we want to eliminate. All the numbers of any number. So here we want to generate all the multiples of any number between 1 and 100. Does that make sense? Try to think a little bit about that phrase. Any multiple of any number between 1 and 100. 2 and 100. Thank you. Yes, very good. So we're going to start from so we're essentially doing the sieve, right? So the first multiple of some number I is going to be I times 2, right? And the next multiples of I are going to be at a distance of I, right? So what is this going to produce? It's going to be produce. First element is going to be I times 2. Then we're going to have I times 3, I times 4, I times 5, right? Because we're adding I to whatever number we get from here, right? This is a range with stepping. I times 2. The next one, we add I. So we get I times 3, right? So these are all the multiples of I. I don't care whether I is a prime or not, right? Because I want to eliminate any number that is a multiple of some other number. So I just pick an I, right? And I start eliminating multiples. It turns out that if I do it up to 8, I've done it all, right? And then how do I get this 8? Square root of 100 is 10, but we're not going up to 10. We're going up to 99, right? So square root of 99 is going to be 9 point something. Yeah, I did trial and error, and I figured that 8 is enough, but I'm not quite sure why 8 is just enough. Because we're skipping 81. But it's actually about the I'll figure it out. All right, so we produce multiples of some numbers, right? That's what we produce here. And then we want those that are not inside there. So that's what we're saying. I want those numbers in this range that don't appear, that are not multiples of other numbers, okay? And we're going to get the primes. So this is a similar way of expressing the sieve, okay? No, so the question is, how do we get rid of 81, right? So it's if I can explain how I get rid of 81, right? Then So if this is 8, so at the point when I is equal to 3, I see. So at the point when I is 8, why is that enough? I is not going to be 8. I is going to be 7 the last time, right? So what does that buy me? When I is 7, yes. So what does 7 buy me? Why is 7 important then? Oh, all right. So I don't need 11 because 11 squared is 121, right? That's the reason. So I have to stop at the, I have to include the prime number that whose square is less than 100. All right, that's my limit. Okay, is it clear? So I need to be able to eliminate 49. Right? In order to eliminate 49, 49 is a multiple of 7, but 49 is 7 or 7 times 7. Right? If I didn't have 7 inside here, here, right? I would not be able to eliminate 49 because I would go to all the multiples of 6, right? And 49 is not a multiple of 2, not a multiple of 3, not a multiple of 5, not a multiple of 5, right? So 49 will be there. I need it to be, I need 7 in here, right? Now, if I wanted, say, up to 150, I would have to include 11 here, right? So I have to go to 12 because 11 squared is 121, which is less than 150. So I have to go to up to the square of a prime number, the largest square of a prime number that is less than my limit, that is less than this guy. Is that clear? But 81 is a multiple of 3, right? So when I is 3, that eliminates 81, right? Then I go to 5, I eliminate all the multiples of 5, so up to 95, right? But when I go to, if 7 is not there, 7 will eliminate all the multiples of 7, and 49 is the only number whose only a multiple of 7. It's not a multiple of anything else. So if 7 is not in there, then I can't eliminate 49. The same with 121, right? If I were to go up to 150, 121 is the only number whose only divisor is 11, right? So it cannot be eliminated unless 11 is inside there. Okay? So this is a much neater way of computing the primes, right? And you can turn it into a procedure if you want, but it illustrates very well the list comprehension. This is what we call collection comprehension, right? It's a comprehensive way of. So I have extracted this expression. You see this one. I have extracted it here, right? So you see what you get. And notice that because, I mean, here you could go and try the difference between a list and a set, right? And if you try it as a list, you're going to see certain numbers appearing multiple times, right? So it is definitely one place where we generate the same number multiple times, right? But if we use it as a set, the collection will be compressed so that everything is contained only once. When it is contained only once, the collection is smaller, so this membership gets to be a little bit faster, right? So it's important to have a list, a set rather than a list, right? And then you can play with this and see exactly all the numbers that are generated. And then notice the fact that 49 is here. And then if you change this to, so this can be just 8, right? And if you change this to 7, then 49 will not be there anymore. And then it would appear as a prime. Okay? So this was the hairy part. Okay. So we went through this part. Strings. All right. So call by value, call by reference. We have already seen this. Just we want to define what it is. So whenever we define something like this, right, we define a function and we have a variable x here, and then we can assign, we can change the value of x, right? So we could very easily do the same f x equals 10, right? So I call f1. So you don't see anything happening, but what you can be sure of is that this 1 was temporarily changed into 10. And you're going to wonder, how is that possible, right? Well, the process is the following. You have a function, and that function is invoked, right? In Python, and actually in every programming language, this invocation will create a special record in memory called an activation record. In that record, we create slots or placeholders for every argument, all right? And then we give those arguments the values that come in here, all right? So I would have a record, a piece of memory, where I have correspondence between x and the value 1. But guess what? That record is actually mutable. It actually can be changed. And I can go in and change that value. All right? But the x that we have in there, it's a copy. The value 1 is a copy of the 1 that I have passed in here. It's not the same, right? A copy is made, and then in that slot, I perform a change. Okay? So, in fact, we're not leaking that change to the outer world, right? One thing I can do is say A is assigned 1, and now I can say FA, right? And some of you might expect that A is changed to 10, right? But that doesn't happen. A is still 1. Why? Because in giving the value of A to X, a special slot was created that holds the correspondence between X and 1, right? And then in that slot, the value of X is changed to 10, and then the procedure is finished, right? And the record disappears, but the original value of A has not been changed at all, so it remains at 1, right? Okay, but let's look at a different way of defining G, and I'm going to expect L to be a list, and I'm going to say L index 0 is 10. Okay, so now I am going to pass in, so I'm going to have an argument B, and I'm going to make it 1, 2, 3, all right? And now I'm going to call G applied to B. What do you think will happen with B? Will it be the same or will it be changed? Yes, 10 to 3, right? So why is that? So we have two types of values in most programming languages, all right? So integers and in some cases strings, definitely in Python strings, are considered primitive values, all right? So whenever we perform this copy that you have seen here, right? Because the value 1 is very small, it takes very little memory, right? And if you have studied computer science a bit in more depth and know a little bit about computer organization, you would know that the processor has registers, right? So it is a value that fits into a processor's register. If you don't know what that is, you can ignore it, right? A processor register nowadays is about 64 bits in size. So whatever is 64 bits in size, in principle, will be copied. Okay. Some other pieces of data take more memory, right? And not just that they take more memory, they take a variable amount of memory. The list can have 3 elements, or can have 10 elements, or can have 1 billion elements, right? So in accessing that list, the code and the processor use the reference to it, okay? And when I say reference, you kind of know what that is as well, right? So when you travel, if you want to visit the city and you have a lot of luggage, you put it in the luggage box in the airport or at the railway station, right? And you take with you the key, and that key has a number on it, right? And the key becomes a reference to your luggage. You can find, again, your luggage if you need to, right? If, let's say you're a gangster and you want to, that luggage contains money, and you want to pass that, you want to make a payment, you only need to pass the key, right? You don't need to actually pass. You can store the luggage away, and you can only pass the key, right? So the key becomes a reference. It's a way. It's a unique identifier that takes you back to the contents, where the contents can be rather bulky, right? So it's a similar concept. The computer's memory has identifiers called addresses, right? The computer's memory is actually just an array, but we're getting into much detail, right? So whenever I put somewhere in memory, bulky as it may be, I get a reference to that place. That becomes a unique identifier. It's like the key. That identifier fits into a register. So it's something that can be manipulated by the processor. So instead of referring to this list by its contents, which can be bulky and of variable size, this guy stores only the address, the reference to that place in memory where the object resides. All right? And when you perform this operation, this invocation, the L that you have here copies that reference. So B is the reference, and again, we're taking B and copying it into L, right? A special record is created, activation record. Inside there we have a placeholder for L, and we say L is a copy of B, but when we say L is a copy of B, what goes there is the reference that is stored in B, which is the reference to this list. Okay? So now L and B refer to the same thing. It's like you go to the this little shop that copies keys and make a copy of the key. Right? So now two people have the key. So then whoever has the key can go to the store and change it, take something from the luggage or put something back into the luggage, and right, that is something that is leaked outside of the procedure. Okay? That is what really happens. This guy goes into the luggage, takes the key, goes to the luggage place, and puts a 10 in the first slot of the luggage. Okay? Now you completed the procedure, and the key is thrown away. That guy had a copy of the key, and that key is thrown away, right? Because the procedure has ended. The L is not leaked outside of the procedure, right? But the luggage is still there changed. Does this make sense? Okay? So this is a very important concept to understand. All right? Those of you who are taking the C class that is following this module, we're going to do that and deal with that a lot there, right? So we are saying that there's two ways of calling a procedure, and actually these are implicit. And in C, they're explicit, right? You can call by reference and you can call by value. Whenever you have a small enough value, right, and you give it as an argument to the procedure, that is a call by value, right? So there's no point in putting 1 into memory and keeping a reference to the 1. 1 is too small, not worth it, right? And actually, even though it's not really true, you can do that with a string as well. So Python considers strings as being elementary basic data types, right? But if you take a collection, something that is big and variable size, then that is placed by default in somewhere in memory, and a reference to that is always used. And whenever we pass that as an argument, we perform a pass by reference, call by reference. All right. So there's 2 different ways of doing things, right?
So first one call by value.
Yes.
Call by
Yes.
the difference is that just one number.
Yes, and if I change this value, this change is not leaked outside. The rest of the world, outside of the procedure, doesn't see that X was ever changed, right?
Almost like a local.
Yeah, it's a local thing, right? It's like you have your personal copy of 1, which you can change as you please, right?
But the second one call by reference because
This is a large amount of data. It's larger, but potentially can be as large as you have memory for it, right? So then B, as you write B equals 1 to 3, actually that's where it happens, right? B equals the list 1 to 3. B will be a reference. Will not be the list itself, because variables are things that should also be the same size as a register, right? So it should be limited to 64 bits. So at that point is where the magic happens. B is already a reference to the list, right? And then there's no difference between this and this, right? A copy of the argument is made, always. A copy of the argument is made, right? But in the first case, we're making a copy of the value. In the second case, we're making a copy of the reference. When we make a copy of the reference, we have 2 keys to the same box. Any participant can go and make changes to the contents of the box, right? As the procedure ends, the second key, the copy of the key, is thrown away, but the changes to the box remain. Okay? Well, if it's the value is small enough, integers, floats, strings, it's going to be by value. So in Python, it's implicit. When you're calling with a collection or with an object, actually, it is not correct to say with an object. So everything is an object in Python, but some are special. So it's not correct to, because 3 is an object, right? We've seen that I can say 3 dot add. So this is what makes it an object, right? The fact that I can say dot something, it makes it an object. But 3 nevertheless will not. Okay? So, but we'll see. So I can put stuff in an object, and it will appear to work as a collection. Same with the dictionary, right? So, for instance, I can say def h. So this is I'm expecting it to be a dictionary, and I'm going to say the dictionary of the string ABC is 10, right? So let me call it now. So C is the dictionary, the 1, 2, 3, 4. Okay. So if I call HC, what do you expect to happen? Well, I mean, nothing visible, right? But if I evaluate C now, again, Yes, so ABC appears as a key now, right? So you have changed C, and there's a, right? This is a case where this is a non-destructive. We say it's a non-destructive update because whatever was there already is still there, right? But we can perform destructive updates, right? So what if my C would have had A, B, C, and here we say 1.2345, right? So then when I invoke HC, then C has changed, right? So I had the key ABC and now it has changed. So this is often the reason of a lot of confusion, especially for beginners. Be aware of it. Right? You tend to overlook side effects, changes that happen to the data after a procedure was called. You will say, oh, I have this function func, and I call it on A, and then I get a result maybe, and then I overlook the changes that had happened inside A as I have called func, right? And by the way, having functions that change the argument, change the contents of the argument, that's always a bad idea, right? Now, how can I avoid this? Right? I can always say hc.copy. So now C is the same. Well, let's change C to something different, right? So now C is the same, right? So that's a possibility to avoid this kind of surprises, right? Now, in some cases, because of efficiency, there's no better way, right? So this is justifiable only when this might be a very expensive operation. So if you have 1 billion records in a list, copying 1 billion records will take possibly minutes, right? Well, not minutes, seconds. But maybe that's too much already. So nowadays you would have machines that would have enough room for 1 trillion records, right? So that copying 1 trillion records from memory, inside memory, will actually take over a minute. Okay? So this explains pretty much what we're trying to illustrate here. All right? So there are actually several types of calls. So call by value, call by reference. There is such a thing called call by name, and so on. But we don't have it in Python, so I wouldn't have a way to showcase it to you. All right. The next thing that I would like to talk very briefly about, and it's also something that we've encountered, is polymorphism. Polymorphism is when we can use the same function or procedure with multiple types of arguments. Okay, so let's look at this, and I'm going to ask you what should x be? Obviously, it can be a number, can be a float. All right. Can it be a string? Yes. Can it be a list? Yes. Can it be a tuple? Yes. Right? So we have several options for x. X can have several types. Okay? Why? Because this notation, square bracket, applies to all those types. Is that clear? So this is what we call polymorphism. Okay? A similar example is the length, LEN. Applies to pretty much anything that is a collection. All right? You should try to take advantage of polymorphism as much as possible. Right? So think of, you're going to say, oh yeah, I need to write this function that gives me something about the list. And then one question as you write that function or procedure, one question that you should ask is, does it really need to be a list? What if my argument were a tuple or a set, right? Can I still use the function? Because then it's more useful, right? It becomes more useful. And most of the time, it doesn't cost too much in terms of programming effort to make it. Okay. This also allows you to compress your code. You're going to often find, oh, I need to write this procedure for a list, and then later you find you're going to need to do the same thing for a tuple. So the right thing to do at that point is to go back to the function that does that very operation, operation for the list, and try to make it work for both lists and tuples, right? So that compresses the code. There's less code to read. So whoever comes after you has less to will be able to understand faster what's going on. Cool? Great. Okay, let's start doing the fun part. So for 04 for part 4, there's a recording. Try reading it just to get an idea. All right, I think it's a bit too advanced for most of you. Those of you who are actually interested on a computing track might find it interesting. And let's try to do a bit of graphics for whatever time we have. The easiest way to do graphics, to draw anything on the screen, is with a system called Turtle, where it was invented a long time ago with a language called Logo, where there was the assumption that there's this little widget called the turtle on the screen, and it moves forward, or it can rotate. Move forward, backward, and it can rotate at an angle, right? It moves forward, rotate a bit, move forward, rotate a bit, move forward, right? And that way we can draw a contour, right? We can also have pen down, pen up. So the turtle continues to move, but it can go down or up, and leaves a trail, and the trail is our graph. All right. The system is in a library called Turtle. We imported and change its name into T, right? So for our use throughout this piece of code, we're going to call it T. So let's see what happens here. All right, so look more carefully at the code. What we're going to do is we're going to draw a closed contour, and we want to fill that contour. So we're going to do a begin fill and a begin end. You can ignore these, right? So some yellow coloring is going to appear as a filling because of that, right? The trail that the turtle is leaving is going to be red, I think. So we're going to do the following, right? For a while, we're going to go forward some number of pixels, and we're going to turn around almost 170 degrees. So almost backward, right? 180 would be completely backwards, right? And this is why it's called star, because we're going to draw a star. So it goes up, and then it's going to go almost parallel, just 10 degrees deviation, right? And then again, and then again, and then again, and then again. And I'm sure all of you have drawn a pentagram, right? So it's something similar, just that the angle is a lot narrower, so we're going to go a lot more times, okay? So let's see this running. And I'm not sure. And you can see it being animated, right? We can, of course, change the animation speed. No, it comes with it. So it's going to end when it goes back to the original point, right? So we have drawn, in doing this, we have drawn a closed contour. So then it tries to color it, right? And then that's what the begin fill and the close fill means, right? There are many examples.
This is the star.
Yeah, so this is a star.
How about the square one? This square, this strong square.
Oh, we haven't done that. That's true. I overlooked that one. And for some reason, this has not ended. I wonder why it should have ended. This poor thing is completely, with the recording that is going on. Okay, so now you see the square, which is all right. So I think we can do a t dot reset, and then we can do square again. Okay. Yes, but I have prepared. So, I mean, you can do them. You can research how to do them. All right. Any kind of geometric form is possible. What I would like to do is do something more interesting. All right. So, have you heard of fractals? Do you know what a fractal is? Hmm? Yes, the snowflake is a fractal. All right. So I'm going to, in order to teach you what a fractal is, I'm going to have to actually use the code. So let's go here. And this is fractal 1. And I'm going to do level 1 initially. And then I'm going to explain what's happening. I can't remember what A is. A is, oh, it's the side. So let's give it a 100. And pen size, let's do a 4. And level 1. Let's start with that. $100 too little. Actually, haven't checked the size of the. So this 1,000 might be too much. Let's try 500. I tried on a much bigger screen at home. So let's say 500 here. Okay, level 1 is already too much. But what I want is level 0 actually. So it's so let's go with 0, right? So we're drawing initially a single line, okay? And now I want to perform a transformation. I want to let's go to level 1 and take whatever I drew at level 0. All right, take whatever I drew at level 0, and the curve that I had previously, I'm going to shrink it to 1/4, right, and draw it here. Then I'm going to turn around 45 degrees. I'm going to shrink this, again the same curve, I'm going to shrink it to 1 over square root of 2, I think, or 1 over 2 times square root of 2. Then I'm going to turn 90 degrees, and I'm going to draw the same thing, and I'm going to again draw the curve at 1/4, right? So I'm performing this transformation. I'm taking whatever I had at previous level, right? And I'm doing this. What's going on? I'm doing this. So this is the previous curve shrunk. This is the previous curve shrunk, and at a 45 degrees angle. Same curve shrunk, and at a 90 degrees angle as before, and this curve shrunk. So now I'm going to go to the next level. I'm going to take what I have now, so remember this, and I'm going to do the same process, right? So this entire thing that you see, right, in 4 segments is going to appear here. Okay? And then it's going to appear here a bit rotated. And then it's going to appear here a bit rotated. And then it's going to appear here a bit rotated, right? So then we go to level 2. It's working now. It wasn't working in the beginning. But yeah, so hopefully it keeps that way. Otherwise, I'll let you know. Thanks for dropping by. Okay, so now we take what we have, and again we do this transformation, right? So I wish I had a screen big enough. That so what I did previously, you saw the animation going very slow, but now I have sped it up. Previously, when you draw the star, you could see the cursor going, right? But because now there are very many segments, I have sped it up. Every 500, so this actually I shouldn't have changed. So it was every 1,000 drawings. So it will draw segments, right? So every 1,000 drawings, you will get an update on the screen, right? So what happens normally is that the drawing happens in a buffer in memory, and then that buffer is brought up on the screen, right? And this bringing up of the buffer on the screen takes some time, not a long time, so milliseconds. It takes some time. If I do it with every single update, then the whole thing becomes very slow, right? So I want to do it instead of every single update, I want to do it every 1,000 updates, right? Currently, we don't have 1,000 segments, so actually there's only one update at the end, this one that we're doing here, right? And then between updates, if we want really to see more slower animation, we can wait a little bit of time, right? So this 0 says don't wait at all. So with this line, you can actually vary the speed of the animation, right? But because we're going to get, so as you can imagine, we're increasing the number of segments 4 times to n. We have 4 segments, right? And every time we're drawing those 4 segments 4 times more. So we're increasing the number of segments 4 times to the n, right? It's exponentially raising. So very soon it's going to be slow, even though we're not doing any, right? So 4. Right? And now what you're going to see is that it gets more and more refined. So from a certain point on, the shape of the curve doesn't change very much, but it becomes more and more lower and lower granularity, right? So the fractal, mathematically speaking, is the limit as you go to infinity of this curve. Okay, so if, when this becomes infinity, this 4 becomes infinity, that's the fractal. We're drawing an approximation. Yes? We're going to, yeah. That, no, you just get better granularity, right? So you can still see segments here, right? So now you can see the animation, even though we're doing very few updates, right? So every time you see a movement, 1,000 drawings have passed. Or 500, yeah. I think I didn't reload, right? And if I'm going to say 10, it's going to be even slower, but not much is going to change. Okay?
Why is it like now it did animation before it just
Because it's too many of them. So it's not that it didn't do animation, it's just that you didn't see any animation. It was happening too fast for you to see, right? But now we have very, very many. Okay? 4 times longer. Right? So if we do 10, we're going to have 16 times longer. So you have the code. You can try it on your own. So what I want to this one is relatively regular, but not very regular, right? You can do one that could be extremely irregular. The important thing is that you take one transformation and you repeat it, right? So let's do fractal 2. I can't remember what it is. It's already more than a week since I've done it. No, at first it's here, and we'll go here. And let's see what we get. Okay, so I have to change again. I have a 4K monitor at home. So all right. Oh, so this is also quite regular. Let's look at the use of color. So we can use color. Okay. So I'm wondering if I'm going to use 1,000 here. How bad is it going to be? The problem is that it's going to go up and down quite a little bit. All right. So now imagine this one doing the same thing, and we have color. So let's go to 2. Right, we get something like this. We go to 3. We get this. Right. 4. Right. So let's try 8. Right. You can increase the size of the pen. And you can pick better colors than I did. Okay. So this one only has 3 segments, so it's a bit faster, right? So we can endeavor to say 10 here, and I'm going to put a trim. The video recording doesn't help. It's yeah. Well, you can play with it. So I'm trying to give you ideas. Why is that? Because part of the homework this week is going to be a contest. So you have to come up with your own fractals. and I'm gonna try to put them somewhere. I'm gonna upload them up anonymously, so don't uh, don't share them with each other. All right. Then all of you can vote, and somebody wins. Okay, and then we're gonna have prizes. How about that? You, the one you like most, right? Use just your, but it has to be a fractal. It has to be generated by code. You can't go in Photoshop and come up with. No, no. So it's got to be, the price is going to be, I don't know, chocolate or something. You judge by what everybody votes as they please. All right.
You have to tell us how you code the fractal.
No, so I'm going to give you one more example, right? So you saw the only so where I'm going to get there, right? But the only thing that you come up with is what I showed you for 500 and for the size of one, for the level of one, right? So we're going to go into the code, right? But the first thing that you come up with is this shape, right? So this is going to be replicated automatically. It's up to you to find one that produces a good design. And you see, from this one, you can't quite predict what you're going to get for the size of 10. So that's the interesting thing that you have to, sort of develop a feeling for it. Let's do the last one, and then we're going to go into the code and explain how they're done. So I came up with them over a couple of hours on a Sunday. So it's not complicated. You can play with them as much as you like. So let's do a 500 here. And actually, oh, this one is already 500. Oh, so let's do a 0 here. Okay, so you see, you just pick up a shape. It's not. Right? It doesn't have to be very regular. The more irregular, actually, the more interesting shapes you're going to get. The more irregular, the more interesting shapes you're going to get, right? So I'm going to say 8 here. This one actually will take quite a bit, so let's say 7. Because it's, what, 7 or 8 segments? Alright, so maybe it's too slow. 6.
No, I think it's clover.
So you get some shape, right? Yeah, protein. So many natural growth processes resemble fractals. Okay. Um, So they become interesting when this is a bit bigger. So I'm going to say 5 now.
Yeah, we take a 4.
And obviously you can use the colors. So the colors are fixed now, right? But you can vary the colors a little bit more. So remember that the shape doesn't change. Well, already by when your level is 4 or 5, you can kind of envisage the shape. The only thing that's going to happen is that the granularity goes. But then there's more mixture of colors and so on. So let's look at how these are done. Okay. And let's start with the simple one. Okay, so it's a recursive process, right? Level 0 is always one line. Okay, and for all the other levels, I'm going to use the previous level, and I'm going to use this argument to be the length, essentially the size of the graph, right? So all the time I'm trying to get a graph of the same size, right? So then I have to look to how much do I need to scale these segments. And it's your choice. But what you typically want to end is with the turtle in the same place every time, right? So for the previous level, okay, you do 1/4 of horizontally, right? So the same graph, 1/4, right? Then we go to an angle of 45 degrees. So you go to the angle up, to the arrow that goes up, right? Maybe I should say you go like this because for you it comes from your left, right? So it's my right. So you go this 1/4, right? Then you go up at 45 degrees, and then you want to cover the projection to be up to the middle, right? So in order to do that, the uh, um, the scale of that should be square root of 2, right? So if you remember your Pythagoras theorem, right? So you would have the right triangle. So triangle like this, right? 1/4. But so this is the original graph on this distance, right? So I'm going to do 1/4. This is the middle. And I want to go up to here. So this point the projection should go to the middle, right? So if this is a divided by 4, this is going to be a times a divided by 4 times square root of 2, right? Then I'm going to turn. So always the turning angle is this, right? I was going this way, but here I have 45 degrees, right? Now I'm going to turn to the right, 90 degrees, right? So from this direction, I'm turning down 90 degrees, right? And then a divided by 4 times square root of 2. So I'm going to go to the quarter here. And then I'm going to go a divided by 4 here, right? So then this process is repeated. So the recursive call makes sure that this is not the segment. This is actually the graph of the previous level. Okay? So this is a very simple pattern, right? 1/4, turn left 45 degrees, 1/4 times square root of 2, turn right 90 degrees, 1/4 times square root of 2, turn left 45 degrees, and then 1/4. Okay? Now, what does this do? Right? So you see this is a helper because a and the level changes. So a from here goes to 8 divided by 4. The level always goes to level -1. What do we want to do here? We want to clear the window. We want to say what a pen size is. So it can be thicker or thinner. That changes the quality. We want to change our our speed. And then we want to put the start in a place where it doesn't go out of the screen. And we want to pretty much fill up the screen, right? So because the origin of the screen is right in the middle, right? We want to move it to the left a little bit so that it goes from like minus 1,000 to 1,000. So that was enough room for. So go to just moves the pen, and you move it to two coordinates, right? X and Y. So the X is 1 minus 1,000, the Y is 0. The tracer is the animation speed, right? So you want, in principle, this number to be large and this number to be small, right? If you decrease this number or increase this number, the animation will be slower and more visible. Yeah. So this is what we do in the next one, right? So you do one segment, and then we change the color. Depending on the level, yeah. So it's up to you. It's up to you. It's up to you.
What's the level?
So each time you go to the level minus 1. So level 0 is a segment. When you do level 1, you take the transformation, and on each segment, you actually put the lower level curve.
Oh, so it's like when you're changing from 0 to 1 to 2 to 4.
Yeah.
Oh, okay.
So as you go to the next level, this segment is not just a segment; it's the previous level curve, right? Which gets scaled.
Of course, you always have to be in 0.
Well, you have to actually go down to 0. So you start with this being, let's say, 8, right? Which is here, the same as this guy, right? And then you keep decreasing and decreasing, and it stops at 0 when it's actually a segment. Okay? Not sure. I think it's a leftover. So you might be able to. So reset will. So clear will just clear the window, whereas reset will also put the turtle in the origin. So clear might just be superfluous. Reset might be enough. Okay, and then it might be the case that there are leftover updates in the buffer that have not been put into the right. So at the end, you always want to end with an update. So the drawing happens in a buffer, and then there's a separate mechanism by which the contents of the buffer is brought to the screen. Right? Drawing into the buffer is relatively fast, whereas taking the buffer and putting it on the screen is much slower. Right? So then you don't want to update all the time. You don't want to update after every single drawing, after every single piece of drawing, right? You want to update much less frequently. Because of that, just a second, because of that, at the end, when the drawing is finished, there might be stuff in the buffer that has not been updated on the screen. So you always want to finish an update. Yes? So what I would want you to do is upload a zip with your best drawing, right? So, and tell me the level, and then I'm going to start it. And if it takes too long, but I see that at least the beginning follows, I'm gonna believe you and stop it before the day ends. And okay.
Is your level gonna be like
So the mixture of colors may be because there's much better definition in colors if you increase the level, right? So depending on that. But I mean, feel free to research fractals on your own. So there's a Wikipedia page on it, and use your fantasy in all ways. As long as it's a fractal, right? So it's obtained by this recursive process. It's acceptable. Okay. All right. And I would have hoped to show you the graph of a function today, but since there's no time, so we're going to do that next time. So there's 2 more weeks left. All right. Remember that. With the assignments are going to have different weights, and they're going to get tougher and tougher. Well, tougher and tougher. There's not much left, but they're going to be slightly tougher each time, and they're going to have a bit more weight each time. So I'm thinking that the last one should have 30 to 35% as a weight. All right. I'm hoping this weekend to do a full, a full grading of everything that is there, and by Monday you'll be up to date, because I have a bit more time this weekend, and I'll be up to date, and then yeah, probably I'll try my best to do it every week, but let's see how that goes. Okay. I will mark. So essentially, deducting points from everything that I think is missing from the right. So there is at this level of coding, there is a perfect solution in principle, right? I mean, you may argue that there's many ways of doing things, but things are so simple that there is a perfect solution. So depending on how much you deviate from that, I will deduct some marks. So generally, I'll be gentle, and I'm going to try to give some feedback as well. Yeah, that's pretty much, because it's very difficult. You're coding for the first time, and it's very difficult to have a pattern, right? And say, oh yeah, for this, I don't know what kind of mistakes we're going to do, frankly. So I'm going to discover, or rediscover the mistakes of a beginner. Yeah. But don't be very worried about that, right? Yeah. Yes. No. So everything that is submitted will get something. So don't not submit, right? Make sure you submit something all the time. Okay. No. So don't draw it, and don't do drawings in Photoshop, please. Submit some code. I mean, you have a very clear pattern here, right? The only thing you can do is take this one and at least take this one, the fractal 3, which is a bit more complicated, right? And vary stuff, right? Change colors, make one segment longer, one shorter. Yeah, there's plenty of territory to be covered there. Yeah, so do that. What's stopping you from doing it? So the code gets longer. You're gonna have more lines here, right? What do you mean semi-right? No, but you're going. Typically, the angles are here. All angles are 90. You see 135. So try 60. Try and depending on how regular the shape is, you're going to get a more symmetric or less symmetric fractal in the end, right? So the more scribbly you make it, the more interesting shapes you're going to get. All right. So this, yeah, well, you can change the angle depth depending on the angle doesn't have to be always 90. Make it something that varies with the level, for instance, right? But so as a principle, you always whatever. So instead of 90, I could make it 90 minus something, right? And dependent on the level. But whatever I make it, right? So I adjust it in such a way that let's say this angle is different now. But then I also adjust the length of this, right? So it's more like this, and I always end up here. It's very important to always end up in the same place. Okay.
Does it have to? Is it a stupid question? Does it have to add up to 360 degrees?
Now,
Oh.
what does it add up to 100, 360? No, I don't think so.
Yeah.
Yeah. Cool. So for the contest, I can give you a 2 week. So I can give a separate deadline for that. If you think that your creative juices need to. But also there is, I mean, once we have a place up for voting, right? You have to do it very fast because I have to wrap this up by the last week, okay, which is 2 weeks from now. Okay, see you next time. Thanks for coming.
Thank you.